1.41 times 10 to the 20 times 6.63 times 10 to the negative 34 cubed, right? Our Planck's constant. And then we get this is equal to 6.3 times 10 to the negative 11, which of course is much, much less than 1. So as expected, we can use our classical statistics for our helium atoms in a room temperature bottle of air or whatever the container is. So, excuse me. So now when we cool this gas way, way down, we're not going to have this 2.24 times 10 to the negative 2 anymore. Right? The density of liquid helium at its boiling point, so at T equals 4.2 Kelvin, particle density N over V is equal to Na molecules So I paused because the book writes this in a really confusing way. So I'm just going to skip over a couple things of what the book says and just write that the density of helium atoms at that temperature is 1.87 times 10 to the 28 helium atoms per meter cubed. Yeah, so we'll take that as given. And we can get that from our NK equals PVT. PV equals NKT. Okay. And knowing the mass of a helium atom. Okay. So now we're just going to plug in those numbers into that same equation. This guy here. And we get 3 times 1.66 times 10 to the negative 27 times 4 times 1.38 times 10 to the negative 23 times 4.2 to the 3 halves and 1.87 times 10 to the 28 6.63 times 10 to the negative 34 cubes, and this is 4.39. So clearly, when we get down to this temperature, we have to stop using our Boltzmann statistics and start using the Bose-Einstein statistics. Okay? So where we see the divergence between different types of statistics is when we get to low temperatures. So if you look at excuse me, graph of energy of those particles versus the distribution, see something like this. So this would be Fermi-Dirac. This would be, so this is 1, this is 0.5. This is Boltzmann. And Bose-Einstein goes up to infinity. Okay? So the Fermi-Dirac, we see fewer photons in lower energy states at low temperatures because they repel each other, right? Pauli exclusion principle. For bosons, or excuse me, for Boltzmann distribution for classical particles, right? get on average 1 particle in each place. And as we cool down a Bose-Einstein statistic gas, well, the bosons can be right over top of each other, and in fact like being right over top of each other. So they can go all the way up to infinity. So in principle, we can put every single boson into the lowest energy possible state. Excuse me, I had to clear my throat. But we've just been looking at this f of E. And if you remember, if we want to know the total number of particles of some specific energy, we have to multiply by the density of states. Right? The actual number of particles is how many particles can have a particular energy times the number of different configurations that allow that energy. So we have, excuse me, sorry. We have this same distribution, whether we call this a Boltzmann distribution or a Bose-Einstein or a Fermi-Dirac. So you could write this equation for each of those, it would be the same. So finding that GE is what makes it possible to find that constant e to the alpha, right, that we have in our Fermi-Dirac and Bose-Einstein distributions. So we need to find what the density of states is for these types of systems. So for an example of finding this density of states, we're going to consider an equilibrium system of n classical particles. Excuse me. So no, I'm not going to do it that way. So if we have classical particles, right? So if we treat these particles as sitting in a cube, right? A three-dimensional infinite square well, we looked at before. The energy of n, x, and y, and z. So one quantum number for each of the dimensions of that cube, right? We saw, and if you go back and look at your notes, when we're talking about particle in an infinite square well, excuse me, we have just n x squared plus n y squared plus n z squared. Okay, so go back and look at your notes if that doesn't seem familiar. Right, this is saying we can have a harmonic mode in each of those dimensions. So imagine we could put photons in there, and then as those photons get to be higher wavelength, right, they realize the higher harmonics in each of these dimensions. So because I can put in any integer number I want for any n, there's many different combinations of n's that give us the same energy, right? Suppose this is n equal to n equal to n equal 2, right? Then that gives me a total energy of 4, 8, 12. Well, then, wait, does this work out? Here, I'm going to pause it and think of something that works out. Okay, I thought of a real obvious, simple example. If this guy is 1, and this guy is 1, and this guy is 2, that's the same thing as if we had this guy 1, this guy 2, this guy 1, this guy 2, this guy 1, this guy 1. So we've got 3 different ways to make up that same energy. Okay? So, oh, I'm out of paper. Pause again. Okay, I got my paper. So if we think of a space defined by energy, right? Defined by the harmonics of different possibilities of energies. So each excuse me, each of these dimensions is going to be one of the possibilities for this equation here, right? So if we think of this as a lattice, and the book has a picture of this, right? sort of point on that lattice separated by how many notches we are over in that particular direction for that dimension of the energy, right? If we want to know how many, so if you imagine filling this out with this lattice, where each of these points along the lattice is an allowed energy state, right? Some combination of an nx, an ny, and nz. If we want to know the possible number of states, excuse me, that can give us a particular energy, well, we say, okay, some particular energy, E, that's going to be the surface of the 8th sphere in this space. So this should look pretty similar to the stuff we were drawing before when we were introducing density of states, right? If we fill in this lattice everywhere in this 8th volume, right, this 1/8 of a volume, right, because we can't have n equal negative numbers or even actually 0, so this point is non-existent actually. In this space, any point on this surface is going to be a different possibility for these 3 different n's that give us the same energy, right? So if we had, say, everything in the y direction, that's the same as if we had everything in the z direction, and any combination in between, as long as we're sitting at that surface. So our density of states, again, is going to be the surface area. So you may ask about this this lattice here. Wouldn't this mean that these points have to sit exactly on this surface? Well, we make the assumption that the distance between these 2 points is really tiny, which it is, because if you think of all the different possible energy states in a box of a reasonable size, well, there's going to be so many. There's going to be so many harmonics that the distances between them in this energy diagram is going to be minuscule. Therefore, we assume that this looks continuous at this surface. So again, our energy given n, right, is E naught, the ground state energy, nx squared plus ny squared plus nz squared. Okay. Excuse me. Okay. So the number of states that have a particular energy So again, I had to pause real quick to understand the book's derivation. So the way we're going to find the volume of the surface is a little weird, and I guess there's reasons for doing that, which is we're going to take the total number of energies beneath some radius, right? So the volume inside this octant of a sphere, right? And then we're going to find, imagine this shell has some, I'll draw it again. So sort of as before, we imagine that this shell has some thickness, right? And it's in this infinitesimal little thickness that we're looking for our state. So this infinitesimal thickness goes all over the surface of this volume, of this deeper volume. So we want to know, right, the energy there, and so that's before this, before we get to the shell, and then after the little infinitesimal thin shell, we're going to have E plus dE, right? So this guy here, this dE, that's what we're going to be looking for, and that's what's going to tell us how many states are in this thin shell, right? That's going to tell us how many states have the same energy, which is going to give us our density of states. So we want first the total energy, which is going to be the volume, right? It's going to be everything in here. So So the number in there is equal to 1/8, right? So this is the octant, right? We're not looking at a full sphere, we're looking at an octant of the sphere, and then we'll have the volume of a sphere. Right, so this is some r cubed over 3, and this is equal to pi over 6 E divided by E naught, right? The current energy divided by the ground state energy. So 3 halves. And then this guy, right, that's going to be dN dE. So that's going to be our density of states. Right, how many things are in there? And that derivative gives us, well, if we go from this energy to this energy, from E to E plus dE, how many more of those energy states do we add? Right, so you can imagine we're going along some line, right? In each position along the line, we're enclosing a larger and larger volume, right? And we get to here, which is the actual surface that we're looking for, right? And we're saying, okay, we had this much energy here, and now, or rather we had this number of states here, and now at this energy we have this next number of states. So the difference between those two is going to be our our density of states. Okay, so hopefully that's clear. Maybe there's a more direct derivation of this. Maybe the next class will be lucky and I'll have figured that out. Anyway, so we take the derivative of this guy here with respect to energy, which at least that's pretty straightforward. Two m 3 halves L cubed, right? The length of the box, 4 pi h bar squared, E to the 1/2, where we've plugged in ground state energy, right? Which is just the energy with all of that stuff equal to 1, right? The minimum possible energy. Now we just want to rewrite this a little bit to make it more intuitive, and combining constants and stuff like that, and we end up with G of E equal to 2 pi 2m 3 halves times the volume h, no h bar, just h cubed, and then square root energy. Right, so we have a bunch of constants, right? Mass, the volume, Planck's constant, and the square root of the energy. So, if we think those particles are electrons, for an example, right? Density of states for electrons. Well, now we're going to multiply this guy by 2, because electrons can have 2 states. So this was for particles flying around in a box, right? But for electrons, there's an extra degree of freedom, which is whether they're spin up or spin down. So if we want the density of states, so we could call this box just a plain box with no extra complications, and the density of states for electrons in that box, we're going to multiply that by 2. So 4 pi 2 mass electron 3 halves volume of box divided by h cubed square root energy. So we're going to need this equation in a second, so I'm going to start. Okay, so now that we've gone through all this density of states business, we can find those alphas we needed to normalize our quantum distributions. Okay. So the way they do that is we know that our number of particles is going to be equal to the integral from 0 to infinity over energy space. So this will be the Boltzmann distribution. Right, so I'll just put a B there to be clear. DE, number Boltzmann, and then we know that total number is going to rely both on excuse me, the distribution and the density of states. So we're just going to plug in our Boltzmann distribution, which I haven't written down yet this class for some reason, but I'm about to right now. Okay, and then if we knew what the density of states are, right, we would be able to do this. So what? Okay, again I pause because the book does something weird, so I'm going to diverge from the book. Right, so the book goes on to say, well, what if these things are electrons, but then continues to use the Boltzmann statistics. So I'm just going to say that I'm going to ignore that if they're electrons business and say, well, if they're Boltzmann particles, if they're distinguishable particles, right? So this would be this guy here essentially. And Boltzmann equals e to negative alpha 2 pi. I don't know why halfway through it says, hey, they're electrons, because that's just confusing. Volume h cubed 0 to infinity dE square root e to negative e kt. So this integral is something that we can look up, or we can do it with a change of variables and a couple other clever tricks. So then we get n equals 2 pi mass kt 3 halves v h cubed e to negative alpha. And if we want to know this alpha, we can just invert this equation. Okay. So in the 1920s, people observed that the behavior of helium gas changed dramatically when it was cooled down to 2.17 degrees Kelvin. Okay? So we can look at our calculation from before, right, a few pages back. Where did I put it? Oh, I didn't even write it down. That's weird. Okay, so we saw from before, right, when we were doing that example, that if we took a helium gas at